Okay. So yesterday, okay, just give me a second. Yesterday, we were discussing at the end about maximum likelihood estimation, right? So maximum likelihood estimation, I mean, this is the general recipe that we have. One second. This is the general recipe that we have. What is happening? Yeah, so this is the general recipe that we have kind of jotted down last day, that okay, if you have some observations for maximum likelihood estimation, you first have to have access to a probability distribution. That is, you assume a probability distribution parameterized by some theta, right? And that theta, what is the most likely theta that have caused the data observation? That is the idea. So for that, what we were doing is that, yeah, just one second. For that, what we were doing is that you compute the likelihood function, and as I said that the likelihood function of the data is basically just the joint probability distribution. Make sure that you have a theta inside it. Otherwise, like, you want to find the most likely theta, that is the theta that maximizes this likelihood. Then you would be very likely to run an optimization method, right? So finding maxima or minima. So with respect to theta, because theta is your maximizing argument there. So if your likelihood function is not a function of theta, then of course it doesn't matter where whatever may be your theta, it will just remain independent of theta. So that is the difference between a likelihood function and the probability that we have seen earlier. So just that you make sure that it's a function of theta, and you just write it as a function of theta, not just some data. I mean, it will be a function of data also, but you need to consider it as a function of theta. Then you just do this argmax, that is, you maximize this L theta. Similar thing is that I mean, for again mathematical convenience, because most of the I mean, this is more convenient in those exponential form of the distributions, but generally it is it generally brings in some other conveniences too. But that is generally the practice, that log likelihood, you take the log of that likelihood, you call log likelihood, and you then try to maximize this. And taking log would not change anything because it's a monotonically increasing function. So the theta that is maximizing your L theta also maximizes your log likelihood, the same. So we have yesterday seen about this, and I think we have intuitively seen what maximum likelihood means for this simple example. Now we were starting yesterday about one very intuitive results that we have probably seen in the very first class of statistics, that okay, if you have to estimate the probability of heads of a coin, then what can you do? You do the experiments, you flip the coin many times, and then the proportion of the number of heads that appears inside that divided by the number of basically the tosses, that gives you the probability of it. So we will see that this actually follows the maximum likelihood formulation. So how to do that? What was the recipe? You need to have the data. So the data is suppose that you have the 3 flips of heads and 2 flips of tails. What is the chance that the head will appear in the next flip? So now, and then you have to have a model that you assume, and then that model is parameterized by some theta, and that theta you are after. You don't know the theta at this point. So each flip you are modeling as Bernoulli random variable x. Now x can take only 2 values, heads or tails. So 1 or 0, we are denoting it by it, and p of that is probability of x given that theta. Theta is what you are after. So theta is the probability of head, right? So when x is 1, that is head, that is the probability theta, and similarly for tail it is 1 minus theta. So we can write this probability more succinctly. Just this is just to write in a more mathematically convenient form, so that you can express this sort of an expression in a single line. So this is theta to the x 1 minus theta to the 1 minus x. If you put x is equal to 1 here in the right hand side, you will see that only this first term will remain. That means that probability of x is equal to 1 given theta is theta, right? And similarly for x is equal to 0, then only this second term will remain, right? So probability of x is equal to 0 is 1 minus theta. So this and this are exactly the same. Now let us go ahead. So what was the recipe saying? You need to find out the joint probability of these data. So let us assume that we have flipped the coin a few times and got the results this. So in that example, it was 5 times, that is n, small n is 5, which are either 0 or 1, either heads or tails. The question is, what is the value of the probability of theta? So this is the intuitive thing that we did in say any of your statistics 101 course. Now we will prove the following with the that the intuition is correct by proving that the guess theta, which is summation of xi divided by n, that is the number of times head appeared, because xi is 1 only for head, right? So this will give you the number of heads. And it is the total number of tosses, is the most likely value for the real theta, that is most likely value for the probability of head. So what is the recipe saying? That you find the joint probability. So the joint probability is of course the product of the individual probabilities, because all the tosses are independent, right? So it is now, I mean, product and I mean the particular form was theta to the x and 1 minus theta to the 1 minus x. Now if you, it was xi of course for the ith trial. So you, when you productify it, or I mean when you take the product of all these i's, these indices they actually become the summations. So this is very simple algebra. Now you go next. So what is what does the recipe says? That we now want to make the theta which makes this probability the highest. So basically as I said, the same theta will also make the log of the probability highest. Now this, you see that if you take log, then the indices come on the left side, and the summation etc they come here. So I mean basically if I go here and you take, yeah, so that is fine. So if you take log, so the sum of xi comes on that side, log theta etc. Even though I mean I don't have to go into this taking log for from +2, right? Now as you may remember, maximizing a function means setting its first derivative to 0. This is again from +2 stuff. So what you are doing is taking the first derivative, which is by using chain rule. So this log theta becomes 1 over theta. This log 1 minus theta becomes negative of 1 over 1 minus theta. This summation xi and summation xi, they n minus summation xi, they remain as the same. Now if you do this little bit of algebra, this is the expression that comes, right? So now you have to make it equal to 0, because that is what maximizing a function means, right? So theta is basically coming, you see this 1 over n summation I is 1 to n xi. So this is what you intuitively do from your statistics 101 course, right? That you toss a coin many times, the number of heads divided by the total number of tosses, that gives you the probability of heads. And that is actually following this maximum likelihood philosophy, right? So this is the maximum likely value of the probability of head. So this is what I think I was trying to mean yesterday. Just I mean I went ahead, I mean went fast yesterday, so I thought of basically explaining it a bit more slowly. So this was the recipe again. Just you have the observations, you basically you express the data as a joint probability, then you take the log and take the maximum. So yeah, so now let us try to apply. So after I do this maximum likelihood for linear regression, then I'll stop for questions. Okay, so this is just 2 slides. So maximum likelihood for linear regression. So we have seen maximum likelihood recipe, how to estimate some parameters. Now, can we actually, or let us see if we treat linear regression problem as a maximum likelihood problem, whether we arrive at the same solution. So does it have a flavor of maximum likelihood, the same thing? So let us assume that the noise is Gaussian distributed with mean 0 and variance sigma square. So you remember, we are now assuming that, okay, there probably exists or a true data generating function, but the observations that you are getting are noise, right? So the data is, I mean, again, I tried to give some intuitive reasoning for such a modeling, is because that, okay, I mean, there are 2 axes in say this say house price prediction problem. So say the number of bedrooms, the square feet area, etc. Now you can take many other basically variables. So for example, say the age of the home, how is the economy going on, what is the state of mind of the builder, etc., etc. But you can probably not take everything into account. So that rest of the thing you can take as the noise, right? So if you could take everything, probably I mean, you don't have to go via this noise model, right, or probabilistic model. But that is the idea, that everything else you take as the noise. So I mean, we have taken the form of a linear regression. So since it is linear regression, the hypothesis is theta transpose xi, and the noise is this epsilon. And again, this noise is making this observation also probabilistic, because this noise is probabilistic. This is deterministic. For a particular x and particular theta, it will always be the same thing, right? So theta is what you are after. Theta is a deterministic thing. It's not probabilistic. X is your input. That's also deterministic. So I mean, the product of 2 deterministic things, or rather a function of 2 deterministic things, that's also a deterministic quantity. But this is where the noise is coming from. The probabilistic component is coming from. Now, a function of a deterministic quantity and a noisy quantity, or probabilistic quantity, will be a probabilistic quantity. So this yi is probabilistic. And this comes from standard results from Gaussian random variables, that if you have if you add a Gaussian noise to a deterministic quantity, that output, the addition also becomes Gaussian, where the mean is this, that is the quantity, the deterministic quantity with which you are adding it, given the mean of the Gaussian is 0. Otherwise, just the 2 means gets added. But here we are assuming that it is 0 mean Gaussian noise with sigma square is the variance. So, and the variance of the addition becomes the variance equal to the variance of the Gaussian. So this is your I mean, the noise or rather distribution of y. So you can write it as a as a Gaussian distribution. So let us compute the likelihood of y. So I see one raised hand. So yeah, Rishabh Tripathi, I'm asking you to unmute. Yeah, any questions?
Sir, as in previous slide, sir, number 10th.
Number
10th, sir, it is 11th. It's previous slide.
Oh, okay. Yeah, I mean, the slide number is probably, yeah.
So this one. Sir, in this case, you just mentioned that if you take all the features, that this error term will be 0. Right now, you mentioned this thing.
Yeah, I mean, if you can take all the possible variabilities, right? I mean, all possible things that can affect this output y. Yes.
But sir, point is that like in this case, we are assuming a linear hypothesis. So this also won't contribute to the error, because this can be any function. So this
is yes. This is linear regression we are discussing, right? So we are assuming that the data is coming from a hyperplane. You can do the same treatment to nonlinear functions, that is theta transpose x. It is not theta transpose x. Say sine of theta 1 plus sine of theta 2 x plus say sine of theta 3x squared, something like that. Okay, that also you can do, but the math will be more cumbersome. That's it, right?
So sir, I'm saying that error, this error term, this is also comprised of that we are restricting our hypothesis to the linear. We are saying that y is equal to theta transpose x plus error.
So do you remember when we discussed about the risk, etc., in the very third topic?
Yes, sir.
So you remember that we said that we cannot search all the hypothesis space. So what
Yes,
you are referring to is the error of that kind. But what I am telling is that even if you know that the data is coming from a linear hypothesis, suppose you know that the data is coming from a linear data generator, but you don't know all the factors that is affecting that linear hyperplane. So how many dimensions is that hyperplane actually is, that you don't know. So what you are telling is true, even like, I mean, if you, what you are telling is true if you don't if you know that okay, it's a nonlinear function data generator, but you are assuming a linear hypothesis, right? But even if you know that it is, or even if somebody tells that no, I know that it is coming from a linear hypothesis, you are taking a linear hypothesis, this theta transpose x, still you will probably not be able to cater for all the variables that is affecting the output. That's what I want to say.
Okay, got it.
Deepak Chaudhary, you have some question, I think. Yes. Deepak, yeah.
Hello. Yes, sir. Sir, I don't understand why this sigma square is remains same for the yi.
Yeah, this is a standard result from Gaussian random variable. So if you have a linear Gaussian model, so to say, that is, if suppose your variable is a and your Gaussian random variable is x, then a is a deterministic quantity, right? Then a plus x is also a Gaussian whose mean is equal to this a plus the mean of x, and whose variance is equal to the variance of the Gaussian. So please go back to the Gaussian random variable, maybe in your very first statistics course that you have taken, you will find this result.
Okay, sir.
Okay, okay. Any questions from Rishabh Chaudhary? So yeah, Deepak, yeah. Oh no, sorry, I have probably asked anyone else. Yeah. Yeah, Rishabh Chaudhary, I have asked you.
Yes, sir. So let us say if xi is coming from some other distribution, say Laplace distribution. Now,
then
what will be the resulting distribution?
Then the noise, that is yi, will be a different distribution, and the maths will be a little cumbersome, nothing else. So Gaussian is just for convenience of explanation I am taking, but the recipe will remain same.
Okay, sir.
Okay. Okay, so let us go ahead. Yeah, you can lower your hand. Okay, so now, okay, let me go to the next slide. Yeah, so so let us compute this likelihood, because we have got the distribution of yi, and this is just, as I said, the joint distribution. Just the thing that the parameters that you want to estimate using maximum likelihood, they are given after this semicolon. Basically, you want to express your joint distribution in terms of them. So, but keeping that aside, if you just try to find the joint distribution, it is the product of the individual distribution, because they are independent. Now, I mean, they are independent means the noise is independent, right? So for each of the noises that is independent, the noise of one observation is not affected by what is the noise for the previous observation, or what will be the noise for the after observation. So that we mean by independent noise, right? Now, yeah. So now you just put the Gaussian expression, Gaussian random variable expression. This everybody knows. Now this pi goes inside, that is the product goes on this top of these indices, right? I have shown in one of the previous slides how to write this as this form. So if I just go back, it was somewhere maybe just before that. Yeah, see. So the similar thing have right. So how can you write it as here, this one, right? So same thing is there. I think yeah, there. So from here to here, if you don't understand, please go back and refer to that slide, right? So this is what we are getting as the likelihood. So what does the recipe say? That you need to take the log of it, right? So you have got the likelihood. Now you take the log of it. So log makes, at least for this case, something's very easy. So this e to the thing and this goes away and so on, right? So you are taking just log from first line to the second line. Now you will do the maximization. So this is the log of the likelihood. And first you try to find the theta that is maximizing this log likelihood, right? So maximizing the likelihood with respect to theta means maximizing this part only, because theta appears only here, which in turns means minimizing this, right? So maximizing this negative thing is minimizing the positive thing, right? Note the similarity with that what we did earlier. So what did we do for the other derivation? That we minimized this, right? The squared loss, right? The mean of the square of the loss, right? Or rather mean of the square of the error, that is the loss. So thus linear regression can be equivalently viewed as minimizing error sum of squares as well as maximum likelihood estimation under zero mean Gaussian noise assumption. So it is not that linear regression can be thought of a maximum likelihood estimation under Laplace distribution, as you said, or some other distribution, or maybe some other model which is not linear. But if you assume a linear model for both of the cases, that is the error sum of square minimizing, and in addition here in maximum likelihood, if you assume a Gaussian noise with zero mean, then they are exactly equivalent, whether you are going via maximum likelihood or via minimizing error sum of squares. But you can ask that, okay, there can be other loss functions. Yeah, there can be analysis for that. Okay, there can be other loss functions in the, say in place of error sum of squares. So maybe there may be some other distributions that can then come out to be equivalent with the maximum likelihood estimation, right? So that way you can do. Now I think oh, okay, yeah, so I'm not doing this because these two are equivalent, so the same same gradient, same minimizing argument will come. One thing I am not doing is this finding the sigma square, but you know the recipe now. You have found the log likelihood. If you try to find the sigma square, you have to take the derivative with respect to the sigma square, try to make equal to 0. If that does not give you analytical solution, then you need to do gradient descent. You can as well do gradient descent using the finding the gradient of this L theta sigma square also, right? So this is this stops the, I mean, I would say concludes the discussion on linear regression. I'll go to logistic regression next, but before that, if there is any question. So I see two raised hands. Yeah, Kaushik, please ask.
Yeah, sir. So just one question, trying to understand it. I think here in the Gaussian distribution where we take x minus mu, right? Or here it's like y minus mu whole square. So here are we assuming the x theta is kind of x theta will be the mean value for y, for that particular y.
Yes, that is the standard result that I am saying, because you see, let me try to explain it at least intuitively. Suppose this was your X and this is Y, right? Now, suppose, let's draw this. So this is your, for this particular X, this is your Y. That is a true Y. Now you are taking the observation, right? So it may be sometime here, it may be sometime here, it may be sometime here, it may be sometime here. So the mean for this Xi is basically this value, this Yi. So actual Yi. So if you could take infinite number of observations for this X, probably that would have given you the mean value. But you are of course not taking the infinite observations for this particular X only, right? So it's a little, I would say it's a little hard to explain intuitively. Rather, it is basically, I mean, it will be a good path if you try to understand it via analytically first and then try to map it back to this intuition. So by analytically first, I mean, it's just a standard result in Gaussian random variable that, okay, if Y is a deterministic quantity and you are adding a noise epsilon, which is Gaussian random variable, then the mean of this sum is the mean of this, basically. Sorry, mean of this sum is this plus mean of this. Okay. And the variance is, of course, I mean, this was not a variable quantity earlier. So it becomes probabilistic or variable as a result of addition of this noise. So the variance of this is exactly same as this. I mean, this can be proved mathematically also. Yeah, I see you have unmuted again. So sorry, muted again. So I'm asking you to unmute.
Yeah. Thank you, sir. I think it's clear.
Yeah,
That's what.
Yeah, I mean, if I find a very some small reference for this, I think I found it in. I mean, found it in. I mean, there are these are in many other books, but yeah, when I took an estimation theory course, I think in Stephen K's book, it has a very good explanation. So I can try to find it and upload it. Okay.
And it's clear also, sir, in a sense that the X theta is then kind of an expectation of Y.
Exactly. And expectation and mean are like, I mean, yeah, I mean, expectation is not exactly same as mean, but yeah, like empirically, yeah, I mean, they can be taken as, yes. Yeah.
Okay.
Thank you. Great. I see another raised hand, Subham, BIT, Sindri, something. Let me see. Yeah, I have asked you to unmute, Subham.
Hello, sir.
Yeah.
Sir, in the maximum likelihood, we are going to take the each data point and try to find theta values. We are going to take all the data points of the training set and find the theta values.
Yeah, all the data points, because you see, you are doing the sum, or rather, you are doing the product here, because what is the probability of a single data point? That is given by this. Now, what is the probability of all the data points? You take the product of this, because the noise is independent.
And
right?
sir, one more question, sir. Sir, how we are going to get this sigma square value?
Oh, yeah, that's what I told at the end, right? So can you tell me, so from here, how did you get the theta value? Just repeat.
By taking just the partial derivative.
Yeah, so how will you get the sigma square value?
Oh, simply taking the partial
partial derivative with respect to sigma, and then sigma square rather, and then
equate it with the 0.
Yeah, equating it with the 0. Yeah.
Okay. Thank you, sir.
Yeah. You can please raise or lower your hand rather, so she can show. Okay, let me quickly go to the logistic classification or regression, that is the classification part. And I'm pretty sure that this has been covered in any of the machine learning course. So I would be a little rather quick here. We have, I mean, I have said in the beginning of the lecture that we have one small logistics related thing that to do after this class. So that is a poll I have created, which I will launch it after the class. I mean, it will be just a 1 minute poll or something. That is, I mean, it will ask you whether you are okay or whether you want to form your own group for the paper presentation, or whether you will want to leave it to me. So 4 students have basically expressed their willingness to volunteer for these logistics to be taken care of. So because they will send you the Google form, etc., to give your choices for your partners, etc., etc. And for that, I need to share your email IDs with them. So if you are okay with this, you just put yes or no. So that will come at the end. But since I think many students were not present at the beginning, so I am just repeating it once more. So now the classification problem. So we have seen the regression problem, basically the idea. Okay, you know what is regression and what is classification. So regression, you are trying to get basically scalar value output. It can be multiple values also, but we are not going into that. It's just the part that we need for basically dive into deep learning. We are brushing up from the machine learning literature. For this classification, we will definitely go to multiple classes, but let us start with the binary classes. So we will conclude this topic with the binary class classification discussion. Tomorrow we'll start with the how to basically extend to multiple class and so on. That we will start tomorrow. Maybe we will not reach there. Anyway, so classification is a problem where again, binary classification, the simplest example, that you want to basically classify your data into 2 classes. It can be termed as many things, positive, negative. That's what I have taken here. 1, 0. So 1 is generally, 0 is the negative class and 1 is the positive class. There may be other names also. For example, a negative class can be a benign tumor. That is okay. You have some tumor data, maybe the images, etc., or size, anything, and you are getting, the labels, so to say, that okay, this data has been for a benign tumor, and the other one is the malignant tumor. So you are just labeling the benign tumor as 0 and the malignant as 1. Other examples are whether the mail is spam or not spam, whether the video is viral or not viral, whether a tremor that you feel, whether it is coming from earthquake or whether it is from some nuclear explosion, underground nuclear explosion that some country has carried out. So these are the features, or I think there were some other terms also called in the very first slide of it. We'll see. But yeah, feature is the common term, at least in deep learning literature, that we will use. So X1 and X2, maybe that, okay, this is for the tumor case, okay, what is the size? Maybe X1 is the size, whatever. X2 is the, say, texture of it, whether it's very fine-grained or coarse-grained texture. And then basically these positive classes are given a label 1, and the negative classes are given a level 0. So this is just, here it is basically shown with different symbols and as well as different colors. So you see that you can draw a straight line in between, and that's kind of a simple decision rule, that okay, if some features puts this a new point here. So if the size is this much and the texture is this much smooth, then you can say that, okay, this is a malignant tumor. Otherwise, maybe some point here, it will be benign tumor, and so on. So that is a very simple idea of classification. Now, where logistics, etc., will come, logistic regression will come later. Let us try to build on this. So as I said earlier, in the next slide, previous slide, drew that linear separator, right? So linear functions can be used to do classification as well as regression. So a straight line can be expressed as a linear function, right? It's a linear parameterization. So we have seen that a straight line can act as a hypothesis function for regression. So where you are, say, generating or have data and you are trying to fit a straight line. And here also in classification, you can use a linear function, a linear hypothesis, to do classification. It will give you the separator or the boundary. So For example, this, okay, I'll come to the example. So what is a decision boundary? A decision boundary is a line or a surface in higher dimensions. Of course, it's not always line, because it's not that always you get two-dimensional features. A decision boundary is a line that separates the two classes, right? Now, a linear function gives rise to a linear separator. So what is a linear separator? I mean, that can be a separator that can be expressed as a linear function. The data that admit such a separator are called linearly separable. So this term will come again later. I mean, why do we need linearly separable and so on when we discuss about perceptron. So basically, some data which can be linearly classified, that is, which can be basically divided by using a linear hypothesis or a hyperplane straight line, they are linearly separable. Which cannot be, I mean, the data set which cannot be done such, they are non-linearly separable, or I mean, not linearly separable. Now, this is one example scenario. This is taken from the Russell Norvig book. I think chapter 18 or something. Yeah, I have not given the figure number maybe, but yeah, you can look at it. So so this is I think the last case that I told in the last slide, earthquake and nuclear explosion. So to measure, I mean, there are many metrics to measure the tremor value, right? But I mean, yeah, I'm not a domain expert here. Maybe some geology, geophysics guys, they can put more information on this domain information. But I mean, there are many types of waves, at least two types of waves that I came to know from this example for earthquake or a tremor. That is a body wave magnitude and a surface wave magnitude, so, or surface wave, basically body wave and surface wave. So they have those magnitudes coming. I think one reaches quickly, another reaches later, and the later one actually does the most damage and so on. But yeah, I mean, that's really the domain expert's job. Now, if you have this body wave magnitude and surface wave magnitude plot for earthquakes and nuclear explosions, so earthquakes are denoted as these hollow circles, and nuclear explosions with these filled-in circles. So you'll see that these mostly the earthquake are on the upper side of this plot, and the nuclear explosions are on the lower side. So you can think that you may find a linear separator. Now, suppose that I mean, I have not told how to get the linear separator, this straight line, but suppose that somebody gives you a linear separator. So suppose the linear separator associated in this figure is this, given by this. So x1, x2, that is, I mean, x2 is equal to 1.7 x1 minus 4.9, which it can be written very well equivalently like this. So the straight line that we have drawn here, this is parameterized or expressed as this. Sorry. So this can also be written in this matrix or the inner product between two vectors, that is the theta vector. So this is the theta vector, this negative 4.9, or rather here, negative 4.9, 1.7, and minus 1. Did I do something wrong? Yes, I think this is a typo. Yes, this should be minus 1. Oh, I'll correct it. Let me, so that I remember, let me just change it to a red color. Okay, and I'll upload that new one. Yeah. Oh, so this is theta transpose x is equal to 0, this form. So now, okay, you see that the values of, if the data point is such that the x1 values are like far greater than the x2 value. Suppose you take this 6 and say this 3, so it will be somewhere here. So this belongs to this nuclear explosion category, and you can also verify it here. So 6 into 1.7 is like 10.2, and so this is minus 4.9 plus 10.2, and x2 is 3, so it is minus 3, right? So this definitely is coming greater than 1, whatever may be the, sorry, greater than 0, whatever may be the value of it. So this theta transpose x is equal to 0 is this, but theta transpose x, if it is greater than 0, then most likely you are getting these tremors from nuclear explosion. And if you just find it here, this 6 and maybe there was some 3 here, or maybe just this 5. If you do this maths, you will find theta transpose x is less than 0 for earthquake. So this will give you a decision rule. Somebody has given the hypothesis, that is this equation of the straight line. Now it's up to you, or you have to see how does that fit into the classification. So that's what basically I'm saying in the next slide. The explosions, that is y is equal to 1, are to the right of this line with higher values of x1 and lower values of x2. So x1 I have taken like 6 and x2 I take 2, 3, right? So they are points for which theta transpose x is greater than equal to 0. So yeah, just to for the sake of completeness, I mean this equal to is given because here you see for the other case it is just less than, because somebody can ask, okay, what happens if it is equal to 0? So it's just to the designer that, okay, where he or she will put this equal to 0. Right, but it's a very I would say boundary case, right? So that's a very difficult case. If something happens here, I mean, how will you classify? I mean, whether it's coming from earthquake or nuclear explosion, right? Now, so the classification rule then you can very well see that if your theta transpose x is greater than 0, then your yx, or what we have called y hat x earlier, that is the predicted value of y for x, it is 1. If theta transpose x is less than 0, then it is that is y hat x is 0, right? So that is how you get the y hat now, right? So you can be very happy that, okay, earlier I was getting y hat as directly is equal to theta transpose x, right? So then what we were doing, y hat minus yi, or y hat I minus y high, I was I was probably giving here, and then you just take a square of it, you sum it from I is equal to 1 to n. You are putting y hat is equal to theta transpose x. Whatever you are finding, that you are taking derivative with respect to theta and equating it to 0. Those things you are doing, or finding the gradient and doing gradient descent. So very well you can try to do this right here also, because it's just that y hat will change to not just theta transpose x, but in this form. Let's see what we do, or what can be the problems in this formulation. But before that, this is a function y hat x, which is 1 for, or rather, y hat x is a function. Rather, if I can say is at y is a function of, say, u, which is 1 if the argument u is greater than equal to 0, and 0 if u is less than 0, right? So this is just I'm trying to give it a functional form, right? A function form. So this is the plot of that function then. So the argument is what I told as u is theta transpose x, right? So alternatively, you can think y as a result of passing the linear function theta transpose x. So theta transpose x was a linear function, that straight line, right? Theta transpose x is equal to 0 was that straight line. But whatever is the value of theta transpose x for a particular x, if you pass through this function, then only you will get the y value, because theta transpose x will not give you the classification level, whether it is nuclear explosion or your earthquake. In case of regression, directly the theta transpose x was giving you the output value. Here it is not. So you can think that y is a result of passing the linear function theta transpose x through a threshold function. So this is called a threshold function. So if it is, the argument is more than 0, then or 0 is the threshold. After 0, y will be 1. After or before 0, or before the value of the argument 0, the y will be basically 0. I think that was what we wrote. Yes. So now to get now as I said, the recipe we saw for minimizing the error sum of squares is basically this, right? What I wrote. Now, to get a linear separator, now I said that somebody gave you the linear separator. So how do you get that linear separator? How do you get those theta values? We have to find theta, which minimizes this classification error on the training set. That's what that y hat minus y square and sum, etc. Right? For regression problems, we found theta in both closed form and by gradient descent. So closed form is that x transpose x inverse x transpose theta or whatever that we got, or the gradient, then finding the gradient and then do the gradient descent. But both approaches required us to compute the gradient. Now here is the catch. How can you compute the gradient of this? Because if you have to compute the gradient of this y hat minus yi, this square, this is I square. So y hat is a function of this discontinuous, or rather this threshold function. It's not discontinuous, this threshold function. So this is not possible for the above threshold function as the gradient is undefined. Here the gradient is undefined at this point. I mean, not the whole point, of course, at 0. When value at x-axis is 0 and 0 elsewhere. I mean, here the gradient is 0, here the gradient is 0, and here it is undefined. So that is the problem for such sort of trying to extend logistic regression to, regression to this classification using the same linear hypothesis. So what we can do is, there is a rule which is called perceptron rule, that the algorithm actually does not compute the gradient to find theta. So it works in a separate way. We will discuss about perceptron in the next topic, which will be tomorrow. But perceptron learning rule can find a linear separator. That's guaranteed. We will also see the convergence rule for perceptron rule tomorrow. I mean, I think probably it will not be completed tomorrow, but yeah, I mean, in the next topic. Given that the data is linearly separable, but if the data is not linearly separable, it cannot find, of course. For data that are not linearly separable, the perceptron algorithm fails. So we need to go for a gradient-based optimization approach for at least, I mean, perceptron, when we will discuss, we will see. But other than this, we have to go for a gradient-based optimization approach. Thus, we need to approximate hard threshold function with this something smooth. So that hard threshold, that was the culprit for not getting, not letting us able to get the gradient. So if we can make it somehow soft, so if this is 0, something like this, I mean, another color, yeah, something like this. Instead of just this hard threshold, if we can go ahead with this, that where the gradients are defined everywhere. So we can try to maybe do some approximate job, where actually it will give to me the probability of a data to belong to class 1 or class 0. We'll see. So that smoothing function, all of you know from machine learning lecture, it is the logistic function. It is defined as sigma u. So this is u, and you can think that this is the sigma u. Is 1 over 1 plus e to the minus u, and it always outputs a number between 0 and 1. So if you have this u very much highly negative, say negative infinity, then this is a very high value. I mean, the denominator is a very high value. So sigma u is becoming 0. If u is, I mean, tend to say positive infinity, then this is a very small value, this one. So it becomes the whole thing, the sigma u becomes 1. And if u is, say, 0, then it is 0.5, right? So that is the logistics function definition, you know. And y, I mean, then what you can say that instead of y being that y passed through that hard threshold, if you pass it through the sigma function, so u is just, you replace with theta transpose x, you are getting so if the theta transpose x is somewhere here, I mean here, I mean you are getting that it is 1. If it is here, you are getting here. But if suppose it is somewhere here, then okay, this may be 0.9. So this value of, I mean, if you get your theta transpose x something like, say, suppose this is 5. So, and say this is 1. So if theta transpose x is 1, then you can say that maybe that data is belongs to class 1 with 90% probability. That is, that's a nuclear explosion with 90% probability. So you get the probability value. So it can be interpreted as the probability value belonging to class 1. This is called a logistic regression classifier. I mean, taken machine learning course, and this should have been discussed. The gradient computation is tedious but straightforward. So what is the, can anybody tell what is the expression of gradient for this sigma u? Just raise your hand. Yeah, Shubham. Yeah, Shubham, I have asked you to unmute. Yeah, what is the gradient of it?
So sigma u into 1 minus sigma u.
Yes, that's right. Exactly right. Thanks a lot. So that we will use for the gradient computation. So I think that is probably the last slide. This one. So yeah, I think one more slide. So mathematically, the probability that an example belongs to class 1 is given by this. So probability of y is equal to 1 given the xi and theta is sigma of theta transpose xi. That's what we have seen in this slide, right? So if we pass this theta transpose x through it, and whatever is the sigma value, that is my probability. So that's what I have written here. The sigma value is gives you the probability of the example to be to belong to class 1. Similarly, y is equal to 0 is just 1 minus that probability, right? Now you see the Bernoulli random variable case, right? I mean, a similar math. I would not say Bernoulli random variable case, but the similar math. So what is succinct in representation of this? This is this times yi, or this to the 1 yi, and this to the 1 minus yi. So if you put yi is 0, then only this the part exists, which is this, and if you put yi is 1, then only this part exists, which is this, right? Now the joint probability. So you find the joint probability, which is just 1 second. Yeah, just 1 second. Yeah. So this is the joint probability of all the labels. Basically, you multiply them, and then so the log likelihood, you take the log likelihood, and then you basically now you have to minimize it, right? Sorry, maximize it, log likelihood. So if you do this math, I'm not going into the details. You take the derivative with respect to theta j. Whatever Shubham told about the derivative of a sigma function, if you apply, you will find this. And this is just the derivative, right? So you can use it in an iterative gradient descent loop. So I mean, this is the partial derivative of log likelihood with respect to theta j. This is the expression, and you can use it for your favorite gradient descent algorithm to find the thetas, right? Any questions from this part? I think we have completed this whirlwind tour of logistic regression. This will, of course, pave the path for our artificial neural networks later. I mean, starting from tomorrow. But first, we will discuss about the perceptron algorithm tomorrow. So, yeah, if there is any questions, please raise your hand. After that, I'll go to that poll for that paper presentation. Okay, good. I don't see any raised hands. So let me actually go ahead with the poll, right? So I am doing it for the first time. Okay. I have to go here. That means, okay. Oh, no, not this here. First, I will stop sharing, then, oh, why is this? Okay, now, full quizzes. So, yeah, I'm launching it. you can see the polls hopefully. I'm just, yeah, I mean, you take part in it. I'm just asking you to, allowing you to unmute yourselves. If you have any problem, just let me know.
Sir, this is yes or no for just sharing the email ID, sir.
No, this is for whether would you like to form your groups by your
Okay.
at the first line. But you, I mean, just a disclaimer that if you say yes, then I have to share the email IDs. Otherwise, I mean, how do they send you the Google form? That's the thing.
Yes, okay, sir.
Sir, a single decision for the whole class will be taken, that
Yes.
either they will go with the
That's
group
the
making
idea
by
of a
own.
poll, right? That's the idea of a poll.
So no, I mean, for the people who do not want to go for it, so will they have to stick for with that, or if the decision is in the favor of making groups by themselves, so they will have to switch?
See, the idea is that again, what I said, that is the idea of a poll, right? Whatever majority will decide, I have to go by this, and that's why I am not forcing you the decision. I mean, I am just going by this democratic way. Now, the thing is that if you can't find it, if you don't respond to the Google form that these students will send you, the volunteers, you will be assigned randomly, just like I would have done. If I mean, following the I mean, if this thing was not there, that is some people opted for or the majority opted for choosing their own.
Yes, I got it. Thank you.
So how many students will be in each group?
Two. That I have told earlier. It's maximum 2.
Okay.
Maximum means maximum and minimum 2.
Yes. Thanks.
So I'll keep it on for 1 more minute, maybe, because I see not all of you have participated in this poll. Please participate. I see that 77% have participated, though there are 100 students joining here.
So where to find the poll?
Can anybody tell, because I don't have the students view who has
It came like a pop-up,
coming
sir.
on screen.
coming
It came
on-
automatically.
sorry,
It came automatically. Means
yes,
nothing
yes.
I had to do.
That should be the case. So just maybe see, go to your Zoom window. Okay, 1 more minute, I will keep it on. Anyway, nowhere in a democracy you get 100% poll.
Sir, I couldn't find the poll option.
Uh,
I missed it, or I don't know.
yeah, maybe you can just try to go ahead with the Zoom. Maybe you try to log out and log in. In that case, I don't have a good answer. I don't have the view.
Okay, sir.
Yeah, I see increasing number of participants now. Yeah, but I think, yeah. Yeah, I see 85% have given, now 86, 87. So probably some people are finding it late. Okay, I'll have to now stop because it's already 1 or 2. Okay, I'm ending the poll. Yeah, how to share the results, download, view results from browser. Don't know what will happen. Okay, I see around 75% is the result, but yeah, let me just try to see if here, yeah, I shall be able to. Yeah, it's 74% have given. I think let me share the result if that is possible. I mean, yeah, you can see the results.
Yes, sir, we can see that.
Yeah, so 74% have said yes. So I'll go with this, right? Okay.
Sir, if we don't form groups, because most of people, we do not know each other because we have not.
That is the idea. When you are a student of which stream? Can you please tell? Some engineering stream, right? So maybe you will go to some industry or academics. There you will be, you will not be, I mean, with all probability, will not be able to, or you will not be working alone. So you will be probably given opportunity to work with someone else, and not always that you will be able to know people. So when you start working, you will get to know. That's the idea. Is a team building, so to say, right? People say. So you will be given the contact number, or rather the contact email ID. You contact and try to contact them. You will at least, I mean, if you don't take anything from this class, one thing you can take is that, okay, I have read one paper very good. I have made a very good friend, right? Anyway, so I'm stopping the share. So the volunteers, I will send you, as we talked yesterday, that if the poll comes out positive, then I'll share things and so on. So I'll do it today. Okay, so we will meet again tomorrow then.
Thank you.
Thanks a lot. I mean,
Thank you, sir.
Yeah.
Thank you, sir.